The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay, I'd like to introduce Shiho Kawashima. Thank you.
Thank you. Good afternoon. So my talk today is going to be a summary of work that was all conducted at Northwestern University. Part of it is my doctoral work while I was still there. Now I'm at Columbia University, and it's also presenting some work by Dr. Peng Kun Ho, who was a visiting scholar from China at the time, and now he's also a faculty member at the University of Jinan. And it was under the advisement of Dr. Keijun Wang at Iowa State University, along with Professor Ho and Professor Shaw at Northwestern University. So I think a lot of speakers in previous sessions and this current session did a really great job of explaining the importance of sustainability in concrete. And a good strategy is to use supplementary cementitious materials, and this includes fly ash. And the benefits are actually twofold. First, by replacing cement, we can make concrete a more low carbon footprint material. But also, fly ash is a waste material. So by the productive use of waste materials like fly ash, we can actually help to alleviate landfill and waste material storage issues. So that's why I think there's a lot of research being geared towards activating fly ash, because ultimately, even though we want a more sustainable material, we still need it to perform. And so from our work, we approach this problem through nanomodification. So the motivation behind implementing nanomodification is there's been a lot of work being done on the use of nanoparticles in cement-based materials, and they've been showing potential to significantly enhance the properties of our material. And this is very intimately tied to its fine particle size. So we look here, this is the relationship between particle size and then the specific surface area that these particles introduce. And nanoparticles are considered to be below 100 nanometers. And you see that once you go sub 100 nanometers, the specific surface area dramatically increases. And this allows nanoparticles to participate in various reactions, or various effects rather. Seeding effect, where nanoparticles help to introduce nucleation sites for CSH to grow, and this accelerates rate of hydration. Filler effects, where nanoparticles are densifying the microstructure. And also nanoparticles exhibit a higher purity, so this enables them to exhibit increased reactivity. And so all these ways, nanomodification can help to enhance the properties of our material. So our rationale was, why not cater this technology towards activating fly ash? Because through the use of nanoparticles can accelerate cement hydration, and this will lead to the production of calcium hydroxide. Fly ash, as a pozzolanic material, consumes CH to produce secondary CSH. So by activating fly ash through nanoparticles, we can accelerate the pozzolanic reaction of fly ash through the use of nanoparticles. So in this talk, we explored two types of nanomaterials, and that's nanosilica and calcium carbonate. So I'm going to go through each of these. And with nanosilica, there's been a lot of work on this particular type. But in this study, we focused on the mechanisms that underlie the effect that nanosilica has on the strength gain of fly ash cement systems. And then with calcium carbonate, the focus was really on dispersion. Dispersion is a very critical issue when using nanomaterials, so there we really focused on the qualitative and quantitative assessment of dispersion, and then the subsequent effect on the early age mechanical properties. So first, nanosilica. So this is a compressive strength gain of 40% fly ash cement mortar with 0, 2.5, and 5% nanosilica addition. Now at the early age, we see that with increasing addition of nanosilica, there's an increase in compressive strength. This is at 7 days. So it's effective in improving the early age properties. Because fly ash, although it can introduce advantages in the long term, at the early age, there's some delay in setting, delay in early age strength gain, and also delay in rate of hydration. So here we're seeing that the nanosilica is helping to offset those negative effects. But at the later age, we see that the rate of strength gain isn't significant, and even at 5%, there's a slight reduction. Now, from a practical point of view, this isn't a critical concern, but we're still interested in understanding why the nanosilica, although it's improving early age strength gain, is having little or even a slightly detrimental effect at later ages. Now, if you think about the system, there are two components that are competing for calcium hydroxide, the nanosilica and the fly ash, because they're both pozzolanic materials. So to better understand this, we looked at CH consumption through TGA. This is CH content with respect to time. Now for plain cement paste, the CH content just continues to increase due to the progression of hydration. Now with 40% fly ash replacement, there is an initial increase, but then it goes down because the fly ash is continuing to participate in pozzolanic reaction. And with the addition of 5% colloidal nanosilica, CH content goes down even further. And again, that's because colloidal nanosilica is also a pozzolanic material. Now, if we just zoom into the first day and look at the CH content within the first 24 hours. Now, this is a plot of the difference in CH in the 40% fly ash cement paste with 5% colloidal nanosilica and then 0% nanosilica. And we see this initial spike, and that's capturing the seeding effect of the nanosilica. Now remember, in a few slides earlier, nanoparticles have different effects, and this is the seeding effect. But then, immediately, it's followed by a decline, and that's due to the increased pozzolanic reactivity of the nanosilica, so it's starting to consume CH. So these results help to explain why the nanosilica is helping to improve the early age strength gain. We also found in SEM results that with 0%, this is the plain 40% fly ash paste, and then this is with colloidal nanosilica at 5%. These are both at 7 months. And the big difference here is this compact coating that develops around the fly ash particle. And EDS results indicated that this compact coating, which consists of CSH, has a lower calcium to silicate ratio. And it's been reported that low calcium silicate CSH is less permeable. So with the addition of nanosilica, it's developing this impermeable coating around the fly ash, and that hinders later age strength gain. And so this helps to explain why the nanosilica is leading to a reduction in rate of strength gain over time in our fly ash systems. So kind of in summary, with the mechanisms underlying the strength gain of the fly ash cement systems modified by nanosilica, they are improving early age strength gain through the seeding effect and also increased reactivity. But at later ages, due to coating, that strength gain, the rate of strength gain goes down. So that was a study on nanosilica. Now I'm going to talk about calcium carbonate nanoparticles. And again, here we really focused on the issue of dispersion, because with nanoparticles, we're seeing these effects because they're nano size, and this leads to the increase in specific surface area that allows them to participate in all these effects like seeding, increased reactivity, filler effect. But if not, they're not properly dispersed, then we won't be taking advantage of the benefits. So here we're really focused on the qualitative and quantitative assessment of dispersion, and then looked at the effect on the early age properties. So the reason we chose calcium carbonate, Dale Benz talked about this a little earlier in the session, but it's been demonstrated that it can accelerate cement hydration, and it can also contribute to chemical effects where it reacts with calcium aluminates and tricalcium silicate to produce its own hydration products. And this has been demonstrated with nanocalcium carbonate particles as well. In this study by Sato and Baudouin, in 50% fly ash cement paste, even though with the addition of microparticles at 10 and 20%, there was no measurable difference. With the addition of 10 and 20%, there was an accelerating effect. And similar results were attained by Dale Benz to accelerate setting. But if you look at the addition level, 10 and 20% is rather high for nanomaterials. So in our work, what we tried to explore is it possible to still exhibit these enhanced effects with nanocalcium carbonate, but at lower addition levels? And can that be achieved through more effective dispersion? So we attempted dispersion through sonication. This is very well accepted to be an effective method of dispersing nanoparticles, and it's a mechanical method. And we compared Horn sonication versus bath sonication. They each introduced their own advantages. With Horn sonication, it's a more energy-intensive method, so it's more effective. But with bath sonication, you can scale, so you can sonicate more material. And in construction, that's obviously very important. So in this process, you start off with the nanocalcium carbonate dry powder, add water, and then sonicate, and then you're left with a suspension. And that suspension is what you ultimately add to your dry ingredients, your cement and your fly ash, to create your paste. Now, this is a mechanical method, and for most cases in dispersing nanomaterials, you need the aid of surfactant. And in the case of calcium carbonate, that was the situation. So in literature, anionic surfactants have been found to disperse calcium carbonate. So in our study, we tested conventional anionic amphiphilic surfactants and also superplasticizers, including a polycarboxylate-based superplasticizer, or PC. And these are anionic, consist of an anionic backbone that's designed to absorb onto the calcium sites of cement, and also has polyethylene oxide side chains that provide steric hindrance. So PC superplasticizers are systematically used in concrete. So the benefit was that we would expect no incompatibilities within our system. And also there's the flexibility of altering its architecture, so you can change the number of repeatable backbones or repeatable units in the backbone, and also the length of the side chains. So one important component of the study is measuring dispersion, and we did this through spectrophotometry. Basically, you have your suspension, and then you measure the absorbance of the supernatant before centrifugation, and then you get an absorbance spectra like this. And then after centrifugation, you compare the surfactant, and then compare the absorbance at a certain wavelength, and that gives you a quantitative measure of sedimentation. So to illustrate this, if you have a perfectly monodispersed suspension, even after centrifugation, if it's properly dispersed, properly stabilized, it should look the same before and after. Now, if it's highly aggregated, after centrifugation, they're all going to crash out. So you can imagine that if you took the absorbance here, it'll be basically zero. And so there will be a big shift down of the absorbance spectra. Now, if it's a mix of kind of dispersed and then slightly aggregated, after centrifugation, some of it will crash out, but then some of it will remain suspended. And so there will still be a shift, but maybe not as dramatic. So we compared sedimentation or absorbance at a certain wavelength and then got sedimentation as a percent. And we explored a number of different parameters, including amplitude and duration of sonication, and also surfactant type and surfactant concentration. And you can see in the lower right that some surfactants just were not effective at all. After centrifugation, it ran clear, so there was no dispersing capability whatsoever. One of the more effective ones, or the most effective one, was the PC superplasticizer. This sample wasn't even subjected to sonication, just passively, very gently stirred. but the surfactant was effective in stabilizing some of the particles, although some of it did crash out. And with sonication, it was improved. So these are the results of just polycarboxylate superplasticizer at a set duration and amplitude of sonication, just varying the addition. So this is in percent by mass of dry nanocalcium carbonate particles. And at 7%, sedimentation is quite high, but as you increase, there is an improvement. And so 90% sedimentation does sound like a lot, but remember, we're subjecting it into a lot of centrifugal force. For the application of casting samples using the suspension, we're more interested in what is the degree of dispersion at the time of casting. And so that's why we recorded retention over time. So instead of subjecting these suspensions to centrifugation, we just let it sit and then monitor the absorbance over 24 hours. And we compare this for both bath-sonicated and horn-sonicated suspensions. This is the initial absorbance spectra, very similar, and then this is the retention over 24 hours. And you can see that within 3 hours, 70 to 80% are still retained. So this means 70 to 80% of the particles are still suspended, and we can cast these samples well within this 3-hour time frame. So from there, we use those suspensions to prepare paste samples for mechanical testing. First, we looked at setting time, which was measured using the Vicat needle test. So this is plain cement paste, and this is with a 30% fly ash replacement. As expected, there is a delay in setting time in both initial and final set. This is with the addition of 1% calcium carbonate nanoparticles. And this was treated with the PC superplasticizer, but wasn't subjected to sonication. But we see that the surfactants do have an effect, and it does shift the setting time up a little bit. Now with sonication, there's a more enhanced effect. So we see two things here. The surfactant is having an effect on dispersion, which helps to enhance its properties. But in addition to that, sonication is also aiding in the dispersion process. Now we also tested early age strength gains, so 1, 3, and 7 day. If you just focus on this plot in the lower left-hand corner, the line indicates just 30% fly ash cement paste with no nanocalcium carbonate. And then the effect of 1, 2.5, and then 5% nanocalcium carbonate addition. And we see that by 7 day, the 2.5 does exhibit an increase in strength by about 20%. So we are seeing an improvement. And there's also an improvement even at 1% as well. But if we look at the 5%, there's some erratic behavior where at 1 day, it exhibits a lower strength than the control. And at 7 day, there is an improvement, but it's less than the 2.5. And this can be explained by issues of dispersion. So if you look at the mix design of each of the pastes, they all have the same cement, fly ash, and water content, and varying additions of the nanocalcium carbonate, and also varying additions of the PC superplasticizer. Now if we look at the mix with 5% calcium carbonate, if we express the PC superplasticizer by percent by mass of nanocalcium carbonate, it's 7%. And the reason we have to limit the PC superplasticizer is, remember, its purpose is to change the rheology of the paste. And so if we add an excess amount, the paste is going to exhibit segregation. So our PC dosage was limited by the rheology of our material. And so we had to keep it at 3.1. And this yielded a 7% dosage by mass of nanocalcium carbonate. And if we revert back to our dispersion results from earlier, we saw that 7% sedimentation was quite high. So the erratic behavior behind the 5% calcium carbonate particles mix can be due to issues of dispersion. And this was confirmed in SEM EDS results. So this is the morphology of paste samples at 7 days with 2.5 and 5%. Just looking at it, there's no striking differences in the structure overall, but in the 5% nanocalcium carbonate sample, there was aggregation, and this was prevalent all throughout the structure. So the decrease in mechanical properties can be attributed to aggregation, because when there's aggregation, those aggregates are going to contain air voids, and that's just going to create weak points in the material. So in conclusion, the calcium carbonate nanoparticles did accelerate setting, and it did improve the early age compressive strength gain of fly ash cement paste, but there did exist a threshold value that was tied to issues of dispersion. Polycarboxylate superplasticizer did show potential for dispersing calcium carbonate, and this can probably be further improved by altering the architecture of the superplasticizer. And with nanosilica, the rate of later age strength gain was diminished a bit over time, and this is tied to low CH content due to the high CH consumption by the nanosilica at early ages, and then also the low calcium silicate hydrate coating on the fly ash particles. I just want to acknowledge the financial support of Tennessee Valley Authority and Oak Ridge Associated Universities, and also Infrastructure Institute of Technology at Northwestern University for supporting this work. Thank you. Are there any questions?
One quick question. You discussed the decrease in the rate of strength gain in later ages. Do you attribute any of that to self-desiccation?
That's definitely a possibility. That is a possibility. That's something that we haven't explored. So I guess the question is the nanosilica contributing to self-desiccation or later ages, so autogenous shrinkage? That's a good question. We haven't explored the effect of nanosilica on the shrinkage properties, but that may be a topic of future work.
Just curious on the contribution of the nanosilica to the pozzolanic reaction. The nanosilica is going to be swamped by the calcium dissolved from the cement, as opposed to the silica that has to be dissolved from the fly ash. So I just really wonder, just to what extent are we getting any pozzolanic action between the nanosilica and the hydroxide ion, as opposed to the silicate from the fly ash?
So the silicate with the fly ash, I understand, happens later on, which is tied to the later age strength gain of fly ash, so the delay in strength gain due to the replacement of cement with fly ash. But with colloidal nanosilica, because of its higher purity, we are expecting a higher reactivity, so earlier effects earlier on. So I don't know if that answers your question.
Right. I just find that to activate the fly ash, the nanosilica, they try to make the connection.
Okay, so I guess the rationale behind the approach is with the nanosilica, there is a seeding effect, which accelerates cement hydration. And with the acceleration of cement hydration, there's going to be the production of CH. And CH is going to be consumed by fly ash because of pozzolanic reaction. So that was the activation of fly ash by nanosilica. Not directly the pozzolanic activity by the nanosilica, but rather the seeding effect.
So I have a question that when you use the sonification method and you add some of the PC in, so have you tried the one without the PC? Is that going to be aggregate it back together?
So the question is, did I try sonication, dispersing the calcium carbonate without any surfactant? I did. That was actually one of our initial steps because calcium carbonate does exhibit some hydrophilicity, which, that introduces the potential of possibly self-dispersing, but the degree of hydrophilicity just wasn't strong enough, and they just crashed out.
Well, one more question, and I think we need to turn the room over to some other people.
I just have a quick procedural question about the dispersion with sonification. You put the dry grain in a solution and then sonicate it, right? So what was there any, special hood or something like that you need to run? Because, people from safety get on people's case when they start doing these things. So if you can give us some brief idea about this.
Yeah, so whenever we handled the nanoparticles, it was in a hood, and even during the sonication process. So after you add the water, you can kind of assume that the powder is just immersed in the solution at that point. But even through sonication, it's put in an ice bath, so there's no evaporation. And also the sonication equipment is encapsulated in a hood as well. So it's a sound enclosure inside a hood. So.
Okay, well, thank you very much.